welcome back. I hope that you had some time to watch the other videos, and I also hope that you got at least 10% of it. And if you have questions about the other 90%, so today is probably a good day to actually ask them. And so now we're going for the final lecture actually that I have for you prepared. And I think it's the last thing that you need to know in order to actually finish your data gathering and everything else. Well, not the data gathering, but the report of the data gathering after the data gathering is done, which is how to do statistical inference on two samples. Because some of you decided to have two samples, decided to compare between two samples, and some of you who didn't, I guess for you, it's enough to all the content until the last lecture. That is all you need, I guess, for reporting on the data that you've gathered or that you're gathering. But for those of you who are actually going to do like the difference between two samples in whatever way, then this is what you need to know. And we're going to build up on top of what we saw in the last lecture, because basically there is a lot of overlap. There's a lot of common things. It's still inference. It's still confidence interval. It's still hypothesis testing, everything. The only difference is that it's a difference. My God, that was a bad one. So now instead of actually measuring the one value of the population, of whatever population or whatever sample that you gather, that you're trying to, estimate this value, this unknown value from the population, this time what you're actually trying to estimate is the difference between the two, let's say the true difference between two means of two different populations. And we are going to actually work with two different populations, and not like two different things measured from same population. Although these things can get confusing, especially for you, because you're doing this very simple data gathering. So sometimes it can get confusing. We can discuss that later. But theoretically, we're thinking about these two different samples that potentially come from two different populations. So we don't assume that they come from the same population, because then it's a little bit different, and we maybe some of you will have to do that anyway. But it's in theory, we're kind of assuming that these things come from two different populations. And the first thing we're going to do is basically just a recap of the confidence interval, because it's going to be more or less the same in this case. The idea behind the confidence interval is still the same. It's still this idea of building this unknown hidden normal distribution. Of course, you don't really have to like draw this distribution or anything. You just have to think that it exists. It is there somewhere. And we know some of the parameters of this distribution, like the center and the width, so the mean and the standard deviation. So we're still going to compute those things, or the standard error actually in this case. We're still going to compute those things, and we're still going to estimate a confidence interval based on that. It's just that the actual way you build this normal distribution, or the actual way that you, let's say, determine this normal distribution, this hidden normal distribution, is slightly different than what we did before. Okay, but the idea is still the same. You have this distribution, you kind of determine it in your head abstractly, and then we go and we say, okay, I want to define this lower limit and this upper limit based on some kind of what we call the critical value. In the last lecture, we didn't really, I didn't really go into details too much on that, because I wanted to do it one thing at a time. So we're always using two, right? So we're always saying, okay, there's like 95% of the data is within two standard deviation or two standard errors from the center, right? So we're kind of like, okay, let's just consider that it's two. But actually, this number two is what we call the critical value, or yeah, the critical value. So that's the thing that's kind of like it changes based on what's your desired confidence level. I'm going to talk about that, but let's just keep in mind that this value 2 is not going to be fixed at 2 anymore. We're actually gonna have to kind of like consider different options for that, and depending on what you want to do. So let's say it's 2, and then you say, okay, I want everything that's within 2 standard errors from the center. So it's minus 2 standard errors or plus 2 standard errors. And this is what we have here as the lower limit and the upper limit, right? But so the idea is still the same. That's still how we're gonna compute it. And before, this is just a recap, right? Before, the way we did this sigma of the X bar here, which is the standard error, right? So it's the standard deviation of the mean. We did it by taking the standard deviation, which is S, and then divided by the square root of the size of the sample, right? And as you saw before, the larger the sample, the smaller the error, because you're dividing by something larger, so the error becomes smaller and smaller. And this is not what we're going to do today. This is just a recap of the one sample, but for 2 samples, this is different. So let's take a look at how to do that. And just so you know, guys, please just raise your hands and ask questions or interrupt me whenever you want. I'm actually going to put the participant list here. And then you can either raise your hand on video, or you can raise your hand on Zoom, and I will look at it. And then as soon as I finish the current slide that I'm reading, I will stop and answer you. And it's very important now today, I think, that you guys really try to follow what I'm saying. So if there is anything here that is completely alien to you and you can't understand it at all, I think it's a good time to ask questions, because you will need to do this on your report. So I think it's, and I mean, of course, you could just do it by using some kind of online tool or whatever, but it's important to understand what's going on, because of course there's the exam also. And this is the quick summary of the steps that you need to take in order to build the confidence interval. Again, there is a lot of this that will be reused today. There's a lot that's similar or even identical, but that's also some things that will change. So it's important to remember this, but it's important also to know that it's going to change a little bit. So first of all, you take your sample and compute the sample mean. That's obvious, right? You take the sample mean because the sample mean is your observations, what you're trying to estimate, let's say, from the population. Then you take the standard deviation of your sample. Again, very simple. We've seen this millions of times, and we call it S, not sigma, because sigma is like if you knew the standard deviation of the population, right? Because we said that, when we use Greek letters, we're actually talking about the population. And so we call it S for the standard deviation of the sample. Then you find the actual standard error of the sampling distribution, which is simply the S that you just computed divided by the square root of the sample size. So it kind of like shrinks a little bit because you're dividing by something. So the standard deviation shrinks a little bit in order to determine the standard error. And the standard error ends up being the standard deviation of the sampling distribution, or of your confidence interval, let's say. Then here, number 4, you choose a confidence level. So here, this is what I was talking about, this thing about choosing the critical value. So for 95%, you can usually use 1.96 or 2. This as a learning thing, is an exercise, but of course later you need to be a little bit more strict or more correct about it. But for learning purposes, usually we just use 1.96 or 2. And this 1.96 or 2, this is what I was talking about, the critical level. And it depends, it's intrinsically connected to this 95% confidence level that you defined yourself. So if you define that 95% is too much, for example, and you want to use 90 actually, then the critical value will change. And if, on the other hand, if you say, no, 95% is too little, I want actually 99% confidence, for example, then also the critical level will move a little bit. And we call it alpha for the confidence level, right? So in this case, we call it alpha, although it could be, I mean, whatever. I'm just using this letter alpha to represent, but it could be something else. It could be like Z, for example, in some cases, or it could be T also if it's a T test. So it doesn't matter. It's just a value here, critical value that you're going to, use in order to determine your confidence interval. And then that's basically all you need. So then you take your confidence interval as being this interval that's centered on the sample mean, because it's like where the thing that you observe that's in the middle, plus or minus alpha, in this case, alpha times the standard error. So 2 times the standard error to the left, 2 times the standard error to the right. If it's 1.96 and not 2, then it's 1.96 times the standard error to one side, 1.96 times the standard error to the other side. And whatever changes, whatever value you end up using for this alpha, you just multiply it by the standard error to the left and multiply it by the standard error to the right. And it's always this symmetric space where you have the same, let's say, the same amount of data to the left, same amount of data to the right. Because the confidence level is always two-tailed, as we say. I guess I also discussed this a little bit about one-tailed versus two-tailed. I'm going to come back to that, but we discussed this during the last lecture about the fact that sometimes you're only looking for something that's less than the standard mean. Sometimes you're the mean. Sometimes you're only looking for something that's more than the mean, or sometimes you're actually looking for both because all you care about is something that's different, right? And in the case of the confidence interval, it's always two-tailed. So when you're computing the confidence interval, you're never computing like just one side or just the other side. You're always computing this symmetric, mirrored distribution to the left and to the right, always. And then that's the basics for a confidence interval with one sample, right? This is what we already seen. But now we're going to talk about two samples, which means that you actually, two samples is exactly what it means. You actually take two samples from different populations. And then after you do that, you actually measure two different means, right? Independently. So like, okay, I have this one sample, I'm computing the mean for this one. I have this other sample, I'm computing the mean for this other one. And now now after I do this, now I want to know, are these means the same? Or in other words, what is the value of mean A minus mean B? It's the same thing, right? So for example, if I say that a certain mean A is the same as mean B, that's exactly the same as saying that mean A minus mean B equals 0. It's just like a substitution. Just take it from the right, put it to the left. And then it becomes mean A minus mean B equals 0. Because of course, if two things are the same, then if you subtract one from the other, you get 0, right? And that's more or less what we're asking when we take two samples, because that's always the null hypothesis. I mean, when I say always, I feel like weird saying always, because always is too much, but I've never seen any other kind of experiment where you don't assume, where if you're doing this kind of hypothesis testing, for example, or a confidence interval, I've never seen any other hypothesis other than both means are the same. And then you want to actually like reject that because you have a hunch or an alternative hypothesis that says that they're different. I've never seen something like, oh, mean A is equals hypothesis, like mean A equals mean B minus 10 or something like this. It's not common. I've never seen that happen before. So most of the time, at least as far as I am concerned, what we are testing for is, are the means equal or not? Are these two things equal or not, right? And one interesting thing that you can think about this is that it will never be like I don't think it's rational or reasonable to expect that your sample, the difference between your two actual samples will ever be actually 0, right? In real world, whatever you're doing, whatever measurement you do, even if you are absolutely sure, like say, that these two things are the same. Like for example, let's say you take two samples from the same population, right? Let's say you go there and whatever it is that you're measuring, you just take one sample and then take another sample from the exact same population. And then you compare the means, they won't be equal anyway. Not the means of the sample, because there's variations in the means themselves, right? So that's why we have a confidence interval, and that's why we have the sampling distribution, because even if you take the same sample, or sorry, if you take two different samples from the same population, then you compute the mean in the same way, and you know that they're the same because they came from the same population, when they will not be the same because there's variance, right? So this is what the hypothesis testing, or the confidence interval in this case, is useful for in this case, is because even though it might be the same, of course the observations will not be the same. So what we need to establish here is a certain interval or a way to test this in order to say, look, of course they're not the same. I measured these two things, they're different, but I'm trying to establish what is the, let's say, acceptance, or how much am I willing to let this vary and still say that they're actually statistically the same, right? That's what we're doing with these kinds of confidence intervals. So in this of course, the confidence interval in this case is more like how much do I expect this difference to vary, but for the hypothesis testing is more like, even though they're not the same, I still cannot say that they're actually not the same, statistically speaking, because it's just like random variance that has between them, right? So basically, that's what we're estimating here. We're not estimating a population value anymore. We're actually estimating the difference between two population values. We don't know exactly. We won't really like care too much about what's the actual population mean for A and what's the actual population mean for B. We won't really touch on that. What we will touch is what is the difference between them. If one is X and the other is Y or whatever, all I care is that their difference is either zero or it's not zero, or one is the same as the other, or it's actually larger or smaller than the other. We're not gonna really focus on what are the actual values for these two population, let's say the true population values for them. It's just a comparison. Now, so let's take a step back and think a few seconds about this. I'm not estimating a population value anymore. All I'm interested in this is in the difference. So I'm asking questions like, is this thing larger than this other thing, right? And the confidence interval of the two samples in this case is basically what we will see in this interval. Although it's still a confidence interval like before, you have still like the lower end and the higher end. But again, what you see from these two things is what's the lower end of the difference and what's the higher end of the difference. So the difference is something that is between these two, but I don't know what are the actual values, okay? If you think about it, you will see that the same difference can come obviously from very different values, right? So 20 minus 10 has a difference or let's say 20 minus 15 has a difference of 5, right? And 10 minus 5 also has a difference of 5. So the difference is 5, but I don't care exactly where that difference came from in terms of the actual values. And again, we're going to build this confidence interval so that whenever you want to report this, you're not just going to report, I measured sample A and I measured sample B, and this is the difference. That's it. No, of course, you're going to have to say, this is the difference, and this is the confidence interval that I can expect the actual true difference to be within. And the first step is obvious, right? You take two samples and extract the two sample means and two sample standard deviations. That's the first step, which is basically just the data gathering, right? Before you do anything else, you just go out there and take the two samples, and then from those two samples you extract the sample mean, the sample standard deviation, which are potentially very different, right? Since you're taking two different samples from two different populations, they are potentially totally different than each other. It doesn't matter. Actually, that's exactly what you should expect, that they should really be different, or at least slightly different, right? So you don't expect them to be similar or the same in any way. If they are, so be it. But you don't expect that to be the case. And again, this is just recap so far. Well, actually, this was not a recap. This is actually new content. We're talking about the confidence interval of two samples, but how to extract the sample mean and how to extract the sample standard deviation, that's a recap, right? Because we've seen that 200 million times already. So the important part here is just to remember, right, that we're taking the S and not the sigma, right? So the S means that this is a sample standard deviation. And as we saw before, the sample standard deviation is slightly different than the actual standard deviation when you know the entire population, which is basically never for the sigma. So you divide it by n minus 1, right? Always remember that you're dividing by n minus 1 and not dividing by n in the in S, not in the sample mean. The sample mean just divided by n because it's the normal thing. So you compute this for the two samples, and then you end up with xa, or x bar, let's say A, which is the sample mean for sample A, and SA, which is the sample standard deviation for sample A, and the same thing for B. So you end up with x bar B and SB. So it's just important to determine, let's say, this names that we're going to use in the next slides, so that you guys are clear with that. We have these four values which are separated between these two different samples. Okay, so far so good. Measurement, gather data, extracted some simple statistics from that. And now we're gonna find the standard error of the sample distribution of the difference. So in the first case, what we did was simply take the standard deviation of the sample and divide it by the square root of the sample size n, right? That was all we had to do. In this case, it's slightly more complicated. And again, this is one of those cases where I'm going to show you the formula and I'm going to explain to you more or less what's the intuition behind this. But obviously, I expect that probably whatever software or online calculator or whatever that you're using in order to compute this will probably do this for you, right? So what to do? What can I do about that? This is what we have, and it's important anyway to understand what's going on, because you must be able to reason about what you're doing. So it's interesting. The most important let's say, fact or detail to pay attention to in this case is that when we take the standard error of the difference between these two things, which is what we need in order to build our sample distribution and our confidence interval, is that even though the operation that we're doing on the means is to subtract them, right? Because we want to estimate difference between the means, so x bar A minus x bar B. Actually, when you compute the standard error, you're not subtracting, you're actually summing them up inside the square root. And what's really happening here is that these two terms that you see inside the square root, they are the variance of the two samples, or the two, let's say, sampling distributions for the two samples. We didn't talk much about variance, because variance and standard deviation are very much almost not the same thing, but they're very strongly connected. And I thought maybe it was not worth the time to really focus on variance instead of standard deviation. But basically, variance is simply the square of the standard deviation, or on the other hand, the standard deviation is actually the square root of the variance. So when we look at this thing over here, then basically the variance is what's inside the square root of the standard deviation. That's it. That's all that it is, the variance. The connection between the variance and the standard deviations is that the standard deviation is the square root of the variance. So anything that's in the square root, that's the variance. While the standard deviation is actually the final value of the square root of this thing. So what we did here was we took the variance of the first sample in terms of the standard error here. So that's the squared standard deviation divided by n, and the variance of the second sample also in terms of the sampling distribution. Then we sum them up, and then we took the square root. So basically, it's a way to say, look, the variance or the standard deviation of this operation of one minus the other, that the variance of this whole thing is actually the sum of the variances of these two individual things. And the reason is that since we're considering two samples at the same time, and these two samples, they were taken from two populations at the same time, these two variances are kind of, let's say, interacting with each other. We have two, how can I say it? We have two sources of variance, both from sample one and from sample two. And since we're kind of like making this one minus the other, then these two variances, they basically are added to become one final variance. Because when you have two different things that have two different sources of variance at the same time, and you're kind of like operating on them together, as we are, because we're doing like the sample mean of one thing minus the sample mean of the two things. And I'm not going to go into the math behind this, because you could expand the two sample means and then make it like that, and then you would see that you would have the let's say twice the variance, so to speak. But the intuition is basically this: the variance of this whole thing, it becomes more instead of less. So because it might be, let's say, intuitive, you might think, oh, if I'm subtracting the two sample means, then maybe I should subtract the two sample standard deviations also, because why not, right? I mean, if I'm subtracting one thing there, I'm subtracting the other also. But actually, conceptually, that's not what's really happening. You don't have less standard, less error or less variance in your data because you've subtracted these two values, right? Actually, you have more, because again, you have two separate sources of variance that are, let's say, being merged into one big, almost like one big data set, where these two things are kind of interacting with each other. Okay. Of course, there's no mathematical formulation behind that. I'm not going to get into the mathematical formulation of why these things is what it is. You could, if you expanded the means and then you kind of trying to consider this as being just one big data set of two samples interacting between each other, and then you would see that the variances actually get merged to each other. But I won't get there. All you have to remember is that I have two samples. These two samples are interacting with each other. And so that generates more variance. So my variance is actually larger than before, okay? And this is the formula. And don't forget that the SA and the SB here are squared, right? We have these two on top of them because they are squared, because that's what actually the variance is the standard deviation squared. And then you sum them up, take the square root, and then you end up with this value over here called the S. I call it the SA minus B. You may find different nomenclatures out there, but I'm just calling it the standard error of A minus B. Okay. Okay, now we have the sample means, we have the standard deviations. From the standard deviations, we computed the standard error, which is just one, right? Because we're going to have one, finally, we're going to have one confidence interval, which is just like the confidence interval of the difference. So now step number 3 is to choose a confidence level. Sorry. To choose a confidence level and find the critical value. Oh, sorry. To choose a confidence level and find the critical value. Now I'm gonna talk about this in a bit more details. Why? Again, I've already given a hint on this. Before, we always used 2, or sometimes I pointed that sometimes it's 1.96, because maybe 1.96 is a little bit more more accurate, but 2, since 2 is a little bit larger, it's also okay, because it just makes it the confidence interval a little bit more open and more, let's say, inclusive. But now, actually, I'm going to show you that you can have different confidence levels. So 99%, for example, or 90%. And that will affect the critical value. And the critical value is this number 2 or 1.96 or whatever. So first you choose the confidence level. And then if it's not 95, even if it's not, well, if it's 95, then you actually know it's 1.96. But in this case, we're going to have to do a little bit more work in order to get this, because you will see why, and I will try to make it as clear as possible. So one important difference between what we did before and what we're doing now is the difference between the Z and the T, right? Um, at the end of the previous lecture, I talked to you about the fact that the Z test, when you just take like a number and you just find the confidence interval using that number, that was not very accurate when it comes to real world data, so to speak, because there's this, depending on your sample size, the fact that you're estimating the standard deviation, the sample standard deviation. So let's say you're estimating the population standard deviation from the sample standard deviation. So you don't know the true value of the population standard deviation, which we basically never know. That then the Z, when you used the Z, that was not really very realistic or very accurate. So the right thing was to use the T instead, right? And the T, what's the difference with the T between the T and the Z is that the T, you depend on that thing called the degrees of freedom, which basically means the size of your sample. So the idea is that the size of the sample itself changes the shape of the confidence interval or the hypothesis test. And so the normal, let's say that the normal distribution kind of changes a little bit depending on what is the size of your sample, right? After 30 or after 40, actually that doesn't matter too much. Actually, if you were to compare the confidence intervals that you would get by doing the T or the Z with like a sample of 40, you will see, or 30 or 40 or something more than that, actually you would see that it wouldn't really make that much of a difference. But with small samples, it does make a difference. And the T is just the let's say the accepted realistic way to compute this. So from now on, I'm only going to talk about the T test or the T confidence interval. And for that, we will always use the degrees of freedom in order to have this critical value or critical score, depending on how, I think, depending on which slide we are in, I will talk about it in a different way. But it's just the critical score, the critical value. So let me take a step back and lay it out for you in slightly slower and slightly more. I will attempt to be more, let's say, clear with this. Even if we consider a 95 confidence level, which is what we did in previous lectures, the actual critical score of 2 or 1.96 will change when you are using doing the T test or doing T, let's say, confidence level using a T, okay? So in a normal distribution, which is like a perfectly normal distribution using a Z, 95% of the data are within 2 or 1.96 standard errors from the mean, always. That doesn't change. And it doesn't matter if your sample size is 200 or 1000 or whatever, it doesn't matter. Different confidence levels have different critical scores, right? For example, if you wanted a 99% confidence level, you would use a critical score of 2.57. Now, what does it mean? Think about this. You have a confidence level, or a confidence interval of 95%, right? So you have the lower, although I think you won't, you see this mirrored, right? So I actually should invert that. So you have the lower end of the interval, and you have the higher end of the interval, let's say, and that's -2 standard deviations or standard errors, and plus 2 standard errors. That's 95%. Now you imagine that you say, look, 95% is actually too little. I want to have more confidence. So I want to have 99% confidence. Your critical score actually has to go up a little bit, and you have to open up a little bit. So it becomes 2.57. So now we are at -2.57 and plus 2.57 standard errors of the mean. And why is it that I made it larger? It's because the larger I make, the more data is in it. I'm including more possibilities in it. And by including more possibilities, I'm more confident that the actual population value is within these two values. So it's basically, when you have a 99 confidence level, you're saying, look, I'm very, very sure that the hypothesis, the let's say the true population value of the difference or whatever it is inside this interval, because this interval is so large at this point. It's 2.57 standard errors away from the mean. So it's so large that actually basically almost everything is in it. And since almost everything is in it, then I'm pretty sure that the actual true population value is in it. So I'm 99, for example, 99% confident that the actual true population value is within it. But being confident doesn't mean that I know where it is. Actually, I know less than I knew before, because there's so much stuff in there that I'm not sure where it is. I just know that it is somewhere in there. I just don't know where. But I kind of give you high confidence, because if you actually take a value that's outside of this 99% confidence interval, then you're like, okay, I'm very sure that this is not the true population value, because it's not even within my 99% confidence interval, which is super large and includes almost everything in it. So if it's actually outside of this confidence interval, then I'm pretty sure that that's not the true population value. Okay. And on the other hand, the opposite is the same. So if you wanted actually to have a 90% confidence interval, so you would shrink a little bit. And then you would say, look, I'm shrinking a little bit. Now I'm only like 90% confident that the value is within this. But since it's a little bit less, then I'm like, yeah, okay, it's actually, I'm less confident that it is actually in here, because it could be outside, because there's a lot of stuff outside. But it's I mean, if I at least have a smaller, let's say, confidence interval to consider. So, but I'm less confident. So it is a trade-off. Either you have a lot of confidence, but too many stuff in it, or you have not that much confidence and not much stuff inside the confidence interval. And that's how the critical score here, the critical value here, that's what it means, right? It's the amount of standard deviations that or standard errors. Sorry, it's standard deviation are basically the same. It's just that the standard error is a special type of standard deviation, right? So it's just this amount of standard errors that I am willing to consider to be away from the mean, so that I actually reach the desired confidence level that I have, either 95 or 90 or 99 or something else entirely. Now, this is what the critical score is. And this is what it means, right? This is this idea, this intuition behind it. However, in order to find it, then that's another thing entirely. So you were not supposed to find it on your own, like with some kind of a mathematical formula or anything like that. That's actually something you're just going to have to find online, or in a software, or in a spreadsheet, or something like that. And that's basically how it is. You give a certain confidence level, and the software or the website or the spreadsheet or whatever will give you a certain critical score. So as you say, I want 95%, and then the site or the calculator or whatever will tell you, okay, your critical score, your T star is 2.3258 or something. Or you say, oh, I want to have a confidence level of 99%. Then again, the spreadsheet or the calculator will simply tell you, okay, then your T star is actually 2.68 or something, or whatever. So basically, that's what I expect you guys are going to do anyway. You're always going to use these online calculators, or some kind of a spreadsheet, or something that you have in your computer. Because that's not, you're not supposed to find it on your own anyway. It's part of the normal distribution, the probabilities and everything else, and you're not going to do it on your own. You're just going to have to take it from somewhere else. But it's important that you understand what it means. Okay. So given your chosen confidence level, 95%, for example, or alternatively your significance level, which is basically the same thing, right? It's just like, okay, if my confidence level is 95%, then my significance level is 5%. And the difference is that 95% is the confidence. So it's how confident I am that something is within my confidence interval. while the significance level is based on the hypothesis testing, is how much I'm willing to accept something to be significant, so that anything less than that is not significant for me. Anyway, it's exactly the same, because one represents what's inside and the other represents what's outside. So if you have 99% confidence level, then obviously you have 1% outside of that, and then that's your significance level. So it doesn't matter. They're both the same. They're both like two sides of the same coin. And that depends on what calculator or what site you're using. They will ask either you to put 95% or they will ask you to put 5%. So it's the same. Then you can either use a table to find it, or one of the many online calculators. I like to use tables because whatever, I don't know why. I guess I like to do it the hard way, but and we're probably going to do it using a table later, but it's just the same. And remember, I talked about it before, but I will say it again. Confidence intervals are always two-tailed, again, because you're always taking the center part and ignoring the two sides of the curve. You're never going to do it only one side or only the other side. So if for some reason you're using a website or something that's fixed at one tail, then you have to use half of the significance level, which is very interesting here to think about this. Because, for example, think about this one little figure that we have here on the opposite, on the right-hand side here. Let's say we're doing 95%, right? So you're considering, okay, I want this part here that is kind of like scratched in blue. I want this to represent 95% of my distribution, right? So let's say I'm going to the left and to the right, and I want to build this confidence interval, and I want 95% of the possible data or the possible values to be inside this area here, right? So that means what? Well, that means that 5%, which is what's left from 95, is outside of that curve, right? But outside means both sides. So I can't say that there's 5% here and 5% here, because that would make 10%. So, and if that made 10%, then the area here would be actually 90% and not 95. So actually, if you say that this is 95, then there's 2.5% here and 2.5% here. And that's why I say that if you're using a calculator to fix it one tail, you should use half of the significance level, because if you're computing it one-tailed, then only the first tail here matters, let's say. Actually, it's usually like this because it's cumulative from the left to the right, but since they're the same, so the same thing you compute here is the same thing here, because they're symmetric, right? So what I mean here is that if you wanted to know this value here, you would actually have to compute 2.5% here and not 5%, because there is actually 2.5% here, not 5, because 2.5 is here and then 2.5 is here, right? So you have to keep this in mind, that if you're trying to compute a two-tailed thing by using something that's fixed at one tail, because sometimes it is, sometimes there are tables that only give you one-tailed probabilities. So you're going to say, oh, I want to know where is my t-score for 5%. Well, actually, you have to look for it for 2.5%. And then it says, okay, it's 92. Okay, great. So then I take, like in this case, it's not really a good example. I took it from the previous slide, but this case is not really a good example because this is not symmetric. It's actually like this is -8 and this is +14. So sorry for this. I didn't pay attention to the numbers here. I just wanted to have a figure that would show something. And actually it looks symmetric, the drawing. So so what happens is that if you want to have, if you're using some kind of a calculator that's fixed at one tail, and then you're trying to find out this value over here, that where is the t, this t-score, let's say, this t critical value, that actually isolates 2.5% to this right and 2.5% to that side, then you would use 2.5% and not 5%. And I hope this is, I will actually go through an example with this, and then maybe it's going to be a little bit clearer to you. And from now on, we don't use z-tests anymore, only t-tests. So you will always have to determine the degrees of freedom when computing these critical scores and p-values. And again, it's basically the same. It's still, you're still going to use a table or a calculator or something, but the difference is that the table or the calculator will ask you how many degrees of freedom you have, because that will affect the actual value that you get. So it's not, from the point of view of someone who is just trying to obtain a critical score here, then it's just one extra thing that you have to feed into the system in order to get the critical score. And you just have to know that your degrees of freedom, yeah, okay. So then okay, you have the degrees of freedom, and you will always have to use it in order to get a T star, let's say, score, critical score, because like I said, the distribution changes based on how many degrees of freedom you have. So different degrees of freedom will give you different critical scores. But when you were, we talked about it also last lecture, when you have just one sample, the degrees of freedom are simply the sample size minus one. And again, I'm not going to get into the math of why that is so, but that's what it is. And it has to do with the fact that you're comparing different things. And when you have just one point, there's no degree of freedom. And the first degree of freedom only comes when you have the second point. So anyway, what matters is that you have the sample size minus one. But when we're doing this for two samples, then actually, unfortunately, there are many ways of doing it, and different places there you go, different, let's say, websites or different books or different calculators will give you different things, and then we'll give you different formulas. So the approach that we're using here is what is usually called the conservative approach, where we're kind of like let's say we're accepting, we're not taking too many risks, so to speak. We're taking the minimum degrees of freedom that we can possibly have in order to have an accurate result. Probably you could find a more accurate number of degrees of freedom if you did a more complicated formula. But in order to keep it simple and to still be conservative and be safe, on the safe side, we're going to use this formula for the degrees of freedom. So it's basically take the smallest sample. So sometimes your sample will, I guess most of you guys are actually taking the same number of samples for both samples. So in your case, it doesn't matter. Actually, you just take a sample size minus one. But in case you weren't, in case like one sample had 30 and the other sample had 40, then you would take the smaller one. So that's what this mean here means. It's the minimum sample size between the two samples. So either, like, let's say if it's 30 or 40, then you would take 30. And then 30 minus 1, 29. That's your number of degrees of freedom for obtaining the critical score here. That's what you would use, okay? And again, that's let's say safe approach for that. And then I have a link here for an example of a one-tailed calculator, which is something that will give you the critical score. So for example, we can take a look at this. Yeah, so it says critical value. You see, sometimes it's critical value, sometimes it's critical score. I guess most of the time it's critical value. I don't know why I decided to go for a critical score. Probably I should have done critical value. So critical value for T, if it's not too small. Look, so this will give you the critical value for T, right? So select your significance level, one-tailed, input your degrees of freedom, then hit calculate for T. Again, you see significance value. It's asking me for significance value and not for confidence level. So just keep in mind that both things are just two sides of the same coin. So if I want a confidence level of 95, then my significance level is 5, right? However, remember that it says here one-tailed, right? So, you know, maybe I can, I would love to actually clarify this to you. So let me see, let me test my whiteboard very quickly, just see if it actually works, and I can actually explain this to you more clearly what I mean. So consider that, let's see, consider that this is our normal distribution, right? whatever it is, it doesn't matter. So if I'm taking a one-tailed approach, then let's say this is my mean, right? So let's call it X bar. And let's say that I want to find the critical score here that gives me a probability of 5%. If it was one-tailed, then this is what it will mean. Let's say this is my T star here, right? What does this mean? This means that 95% of my data is in this part of the graph here. And 5% is here. So basically this is how the T star, let's say this is what the T star here, the critical score, the critical value means. It's the value here, it's this value over here, actually, this guy over here, that says, okay, in order to have 5% of the distribution to the left and 95% of distribution to the right, this is the value you need here in terms of how many standard deviations you should go to the left of the mean. And this would be your T star here. But you see the problem. The problem is that this is one-tailed. This is so basically I have 5% at this side here, at this point here, and then I have 95 to the entire thing. But that's wrong. That's not what we want. Wrong. For confidence level at least, right? For our confidence interval. This is wrong for a confidence interval, because for a confidence interval, we want two tails. We want something in the middle here. So again, let's say this is our X bar. We want this thing here to have 95%. All right. But we want this. Oh, sorry, not 5%. We want this to have 2.5% and this to have 2.5%. Because if I do this one plus this one, then I have 5% outside of the confidence interval and 95% inside the confidence interval. So that's why, and if you think about it, this, if all I'm interested in is in this T star here, this is what I'm interested in, right? Nothing else right now at this point. So this is actually equivalent to having a one-tailed thing here, and I just take 2.5% here. And this will give me, well, the T star here. And this would mean that all this part here, this has 97.5%. And this here has 2.5%. I don't care. The fact that this thing here is 95%, that doesn't matter to me. What matters is that I found this value over here, this T star here. That's all I want. So I will put 2.5% as if I was doing a one-tail test of 2.5%. And then I will just take that and say, okay, I just take that and I'd use it in both sides, the same, because it's symmetric, so it doesn't matter. All right. And that's why, so let me see how to stop this thing. Yeah. And that's why we have, how do I go back to my share now? I don't know. Oh, man. Oh, yeah, share screen. And that's why I will come here and I will say, actually, my significance level is 0.025, which means 2.5%. And then it asks me for the degrees of freedom. So let's say, let's think about this example where let's say I had two samples of, one is 30 and the other is 40, right? And I say, well, yeah, my degrees of freedom are 29 because my smallest sample is 30 minus 1, 29. And then I calculate for T. And then it gives me here, the critical value is one-tailed is 2.025. 2.045. So you see, it's almost 2. It's a little bit more than 2, right? And that's because the sample is close to 30. But anyway, as you can see here, so this is my critical value now. So what does that mean? Well, it means that if I go back to the slides here, it means that in order to reach the left-hand side here, I would use 2.045 times my standard error. And to go to the right-hand side here, I would use 2.045 times my standard error again, right? And we will do that in an example very quickly, hopefully. And yeah, that's it. That's all you need. Your confidence interval is then the interval centered on a sample mean. And actually, this is not sample mean here. I guess I oversimplify this. This is actually centered on your difference of the sample means, right? Because that's what you're actually trying to estimate here, not that because you have two sample means. So it's sample mean A minus sample mean B. That gives you one value, whatever it is. Then you put it there as in the center of your interval, plus minus the critical value times the standard error. So again, like, yeah, this is the final form. This is the final form of your confidence interval. So this is a little bit more accurate, which is identical to the one we're used to, but with, or let's say then it's almost identical, but with the difference in here. So this is X bar A minus X bar B. So the difference between the means plus or minus our critical value that we just computed. So for example, 2.045, if you had 29 degrees of freedom, times the standard error that we computed over here, this one, which is the pooled variance. So that we call this the standard error using the pooled variance of the two samples. And this is your final form here. And I hope this is not too scary for you, which because we kind of went through very in like, let's say, very slowly through each of these terms, and we're going to do an example so that maybe you are a little bit more familiar with this. So this is will give you an interval, of course, because it's minus to one side plus to the other side, given your confidence level, again, because your confidence level here determined your critical value, right? Depending on your confidence level, the critical value here will either shrink or become larger. And this is what represents that. You can expect to find the actual true value of the difference of the means. So this is where the true difference of the means will be in, based on your confidence level. Yeah, and then some stuff, some quick notes, like remember that since we're using a t-score instead of a z, this is correcting for the fact that the standard deviation is estimated and not known. So what do I mean here? What I mean is that if in a perfect world, which will never happen, you actually knew the standard deviation of the population, again, that will never happen, but still, theoretically, then you wouldn't use a t, you'd use a z. And the difference is that the degrees of freedom will not matter anymore. So the sample size doesn't matter because you know the standard deviation, so you're not estimating it. And in that case, it doesn't matter anymore that what's the sample size. It's fixed. It's always z is always z. So if it's 2, then it's 2. And if it's 1.96, it's 1.96, and that's it. And that's what we've been doing so far before. Although that was kind of like not really realistic. So I was just doing that for like learning purposes, so to speak. And yeah, so and just remember that a confidence interval tells you where the true value might or might not be, but not where it is, right? It's an interval. I say it might be in there and it's probably not outside, but inside the interval, I don't know where it is. Could be to the left, to the right, in the middle, somewhere. I don't know. It's always a higher probability that it's closer to the middle. That's why the curve does it like this and then goes back. And the curve here means probability, right? So the higher the curve, the higher the probability of something being in there. So there's always like, it's probably near the middle, or not probably is not a good word, like it's likely to be near the middle, but I don't know exactly where it is. And that's not why you use a confidence interval anyway. So that's why I want to make sure that you guys don't think in terms of trying to find where it is. You're just trying to find it might be in here and it's probably not outside of here.